Okay, so welcome back and to the third session of Generative AI, and we are going to continue where we left in the first session. So uh, there is little slight modification in today's schedule. Instead of this session was basically earlier was proposed as a hands-on, assuming that this portion will be completed in the first session itself, but we are extending the part of transformer into this session. So we are clubbing today's hands-on session with the hands-on session which is scheduled tomorrow in third session. So all the hands-on related to language models and other uh, uh, advanced model, we are going to have a hands-on tomorrow. Okay, so continuing to the topic where we left. So we started with language models. Then we studied about sequence to sequence modeling, specifically where focusing on the task where we are discussing about the text generation part, and there were some limitations so that there is an improvement we studied sequence to sequence with attention mechanism, and still there were some limitations that we studied that we moved towards, that the new progress have been made for the transformers. And the transformers have been the backbone for all the LLMs that are there. So we'll discuss about the transformer now in this session. So there were main problem with the RNN, even if we are using attention mechanism. There is the slow processing, right? Because we are moving sequence to sequence, we are moving word by word. The processing is not parallel, and the computation becomes very slow for large, long sequences. So this transformers improve on RNN using self-attention mechanism, which is the foundation for most of the NLP models and LLMs. We started discussing, so we are going to discuss this architecture in detail. However, we started introducing this architecture where the main component was the input, embeddings, positional embeddings, positional encoding we add to make the embedding positionally aware. And there are some number of times some components have been repeated, like multi-head attention and feed forward, and these two repeated multiple times, usually 7 to 8, and this becomes your encoder, and the output of the last encoder goes to the multi-head attention in the decoder part. And in the decoder part, it's usually same. However, one additional mask multi-head attention is introduced, and then multi-head attention which takes encoder output as well, and then feed forward, and this is repeated multiple times. And a linear layer and the softmax layer for the output. So we are going to discuss this in detail. So what is transformer? So if we discuss about the transformers, that are the deep learning models that uses self-attention to process sequences and to address the limitation of the earlier model like RNN. Unlike RNN, which process sequence step by steps, transformer can handle entire sequence at once. So, and this because of this self-attention mechanism that we have. And this makes them faster and more efficient, especially for the long sequences. And transformer is the is actually the foundation and the backbone of models like BERT, GPT, T5, and their application uh, it exists beyond the text to the image as well using vision transformer. So we discussed this in detail where RNN struggles with the long sequence due to vanishing gradient problem. And though one of the version of RNN like LSTM avoids this uh, by using some more mechanism and concept like input gate and forget gate, so we are not going to detail of this. But still, LSTM also produces the output of the same length as an input. So not suitable for the task like translation. And we had discussed the encoder-decoder architecture, which struggles with the long-term dependency due to the context vector bottleneck. So we have seen that after encoding the context vector that is fed to the decoder part, uh, have a fixed length and it fails to capture the information or in case of long range dependency. So we introduce this attention mechanism where decoder side, instead of only using last hidden state as a context vector, attention mechanism at decoder part uses all the hidden states and find out the relevant part of the input sequence. But it is still required sequential processing. That is the main problem with the sequence to sequence model. That's where transformers comes into the picture, which enables the parallel processing of the sequences. And just to give you intuition, when we talk about parallel processing, most of the algebraic operations can be performed in parallel, like matrix to matrix, matrix to vector, and vector to vector. So transformer takes a alternative way to maintain that sequence, and still it is able to come up with the idea so that uh, the computation can be done in parallel. So in this architecture, starting with the input embedding. Input embedding is nothing but for each input, we have a word vector, which we had discussed earlier as well. So we map each input token to a vector before applying positional encoding. And we had discussed about it, that why we need positional encoding in transformer, because in case of transformer takes all the sequence at once. So somehow we need a way to track uh, ordering of the sentence. For example, let's say uh, the model should be able to differentiate between the cat is on the mat and mat is on the mat is on the cat. Those two sentences contain the same words but having different meanings. So to ensure that the model understands this sequence order, we add the positional encoding. And this is typically done using sine and cosine functions of different frequencies, which create a unique pattern for each position. And these patterns are added with the embedding so that model basically transformer is able to learn the position aware representation. We'll discuss in later detail in later. So when in the encoder side, transformer architecture is built on the stack of encoder. So there are multiple encoder layers are there, and this encoder processes the input sequence through the multiple layers. So you might have n number of encoding layers for the input, and each encoding layer contains two sublayers: self-attention mechanism, self-attention layer, and the feed-forward layer. This is the important part, which basically gives you the a rich and higher representation of the input. And after each input, the output of one encoder is passed to the another encoder layer, which again contains the self-attention and the feed-forward. And multiple times you repeat it, and the last representation then decoder uses to generate the output sequence, one token at a time. So generative, so decoder stack generates the output sequence using encoder output. So it takes the encoder output, and again it uses self-attention mechanism and encoder decoder attention and the feed forward. So there is one some extra layers are there in the decoder side. For example, consider this thinking machines. So X will be your input, which is an embedding, and Z will be the contextual embedding after the self-attention mechanism. So it is similar to the part that we had discussed about the context vector generation. After calculating the attention weight, multiplying with the softness score, and then you get, so sorry, context vector that is calculated by the multiplying the hidden state with the softmax score. Here the self-attention mechanism, somehow that we are going to see how it does, it generates the contextual embedding, which contains the information about semantical meaning and the context information of the words. And this is passed through feed-forward network, which gives you the encoder representation, which basically goes to the second layer, and the same process is repeated. What actually self-attention do? So self-attention basically allows each token in the sequence to attend to the other tokens. For example, uh, in a sentence, the animal didn't cross the street because it was too tired. So inside the same sentence, self-attention, basically what it does, it computes the attention between the words. For example, here it is highly relevant to the animal word. So the word is it focuses on the most on the animal, not other. So that's how self-attention computes these weights dynamically to enable the model to focus on the most relevant part of the sequence for the input tokens. So to understand it, so how, so what is the, so how it does? Basically, the idea was earlier in RNN, what we are doing, we are giving one word at a time, and we are generating an output, and then the context vector is passed to another RNN unit, and then it generates the output. One by one, it is doing. If we want to perform parallel processing so that computation can become faster, somehow we have to change this mechanism into some algebraic operation. Means if we can come up with a computation in terms of matrices, then we can perform those matrix operation in parallel. This is the basically whole crux and the idea of this transformer architecture using self-attention. So what it does, how self-attention is score is calculated. So there are three vectors are there: Q, K, V. represent query, key, and value. So for each input token, we come up with embedding, and with this embedding, for each embedding, we calculate query, key, and value. So these vectors are calculated. And how it is calculated? They are calculated using uh, some weight matrices that you can think of as a neural network weights, and these weights are learned during the training time. So basically, from each embedding, we come up with query, key, and value. Similarly, for this embedding corresponding to token machine, we have query, key, and value pair. And using the query and key, so this query vector is used to compute the similarity with all the keys. So it computes the similarity score with uh, its own key as well as other keys that are there in the token. For example, sentence have uh, word 1, word 2, word 3, and so on. So query corresponding to word 1 uh, is used to calculate the similarity score with key of word 1, word 2, and so on. So how it is done? So first, a similarity score is calculated, which is nothing but dot product of query and key, which somehow, let's say, for example purpose, it is shown it is 1, 1, 2, 2. And similarly with this query, we using key 2, we calculate some score. And to make it computationally efficient, we is to make it normalized, we divide it with the under root of dimension of the key vector. So here, for example, assuming that this this key dimension is 64, which makes under root of this is 8, and if we divide this score with this, we get a normalized value. So where this dk represents the dimension of key vector, this basically scaling why we are doing this scaling. So this scaling prevents the dot product of becoming too large. So this dot product should not become too large, so we divide it with the scaling factor. And on this scaling factor, we apply a softmax function to squash it and to get the probabilities. And basically, this becomes your attention weight. And once you calculate the attention weight, we multiply it with the value vector to get the context representation. So this output of each query is basically, and similarly, this is done for with the second key and third key and so on. And intuitively, the attention mechanism that we have discussed previously, where higher the softmax score, basically says that this word is relevant to this particular word. So current in this particular example, thinking obviously is relevant to the word thinking as well, and it might be relevant to other as well. So once you have those value vectors, you add those value vector, you get one particular context representation. Similarly, parallelly for word token 2, this same thing is calculated, and it also come up with its own vector. Z1 is computed by adding which components? So softmax values, and the softmax into values, you give the vector v1, right? Value v1, and similarly value v2 is because hum query ko, so we are assessing this query with the key 2 as well, means the second token and third token. So you might be getting v3, v4, and also you add all those vectors to come up with the contextual representation 1. Similarly, for other token, again in parallel, this operation can be done, and Z2 is come up for the other token. So that basically Z1, Z2 represent the contextual information with respect to of thinking with respect to which word it is more closely associated. So we add all these weighted by attention weight to get the Z. So this metric basically we can think of it as a matrix representation as well. So you can see here all the tokens vector, all the tokens and their corresponding embeddings are stacked together, but multiply with a weight matrix, which is nothing but we are, and the value of this weight matrix are learned during the training time, and you get a query matrix, which is first vector represent the query thinking, query machine, and so on. So this whole you can think of as a query matrix. Similarly, the same embedding when multiply with another matrix for linear transformation, then you get key matrix. And for value, you have another weight matrix. When it is linear transform, you get the value matrix. So using matrices, basically you can perform those operations in parallel. That's what the idea, to have an alternative approach to come up with calculating attention mechanism. So overall what it does, so you have a query matrix, you calculate the dot product with key matrix, and you scale it using some scaling factor, which is under root of dimension of key, and you squash the result using softmax, and whatever the output you get, you multiply with value matrix to get the set matrix. Okay, so okay, so there are two questions. Let me answer them one by one. So, why we need these three parameters, query, key, and value? Is it beneficial for further evaluation metrics? So okay, so we are not using it for the evaluation metrics. We are uh, using it for the computation part. So we have an input. So you have an input, which is the positional aware embedding. Till this point of time, you're clear. For example, x, x1, yeah, you can say w1, w2. Now, on the word embedding itself, I want to transform into some matrices, and the idea comes with the search technique that we have. So basically, we want to find out this w1 word one, how it is closer to different, or how it is relevant to different words, w2, w3, w4, w5, w6 in the sentence. So it so it how should I phrase it? Uh, it has the motivation from how we search in when we want to search anything. For example, let's say in case of you want to find out some video lecture on YouTube, right? So you write something which uh, when you write on the search bar, this becomes your key, right? And when you give the key as an input, you get lots of options, right? And from those options, you match this with the sorry, this is your query, that query you give, And for each output that you get in the YouTube, you have the key. Key means the title of that lecture, and you compare, okay, so which is relevant to you. So you match it with the key, and the one which is very much similar to you, you check the content, which is basically the value. Similarly, idea was to somehow convert this input to into some key value pair kind of thing. So that's why we transform this embedding into key and query pair. Similarly, we have another value which represent the value or the content of this embedding. So we transform input into these three parameters: key, query, and value for the computation purpose. So basically, the summary is we are using alternative approach for computation part. And the second question, so it depends. Dimension of key, query, and value depends on the neural network that you are going to train to learn those parameters. Basically, the weight matrix, size of weight matrix, and the size of embedding. Okay. Okay. Any other question? So again, just to give recap, we want, so this key, query, and v value, basically they came into the picture to for finding out alternative approach, so that we can perform those computation in parallel instead of using one by one. So we are transforming each word embedding into uh, three matrices. So another question is, okay. Dimension basically depends on the what is the input embedding you are taking and how you are representing the embedding, which model you are using to embed the input, whether it's a one hot vector or anything. Right. So by doing so, so this weights of these matrices can be learned during the training time, and during the training, these are adjusted so that this query represents, once the training is over, this query represents this embedding this query is relevant to embedding, this key is relevant to this embedding, and also the value is relevant to this embedding. Now, one self attention might be focusing on whether how this thinking word is relevant to some other words. You might have multiple self attention head. Similar to convolution, when you have studied CNN part, you might have seen that you might have multiple filters, filter 1, filter 2, also known as kernel, kernel 1, kernel 2, and those two kernels are focusing on different parts of images. Similarly, you might have different heads for self attention that are focusing on different parts of the uh, data. For example, one head might be focusing that this it is quite closely related to animal, and another head might be trying to capture the different aspect that it is closely associated with the word tired. So one head attends to animal, second head attends to tired. And it is called self-attention because we are looking into the same sentence and which word is associated with each word. And all these attentions runs in parallel multiple times, and each head captures the different aspect. So since having a matrix representation give you benefit of parallel processing. So for example, one attention had 0, it has its own query key and value matrix, and second attention have its own query key value matrix, and different attentions calculating different context representation, they might which might be focusing on different aspect of the input. So this attention calculation can be done separately in 8 different attentions. So here is an example from 0 to 7. There's 8 different attention self-attention head that those are focusing on different parts of the input. And output of this multi-head attention is passed through feed-forward network. And when we say passing through feed-forward network, then it is nothing but we are multiplying with the weight matrix. So we multiply with the weight matrix denoted by WO, which is for the output that was trained jointly with the model. And the result would be the Z matrix that capture the information from all the attention head that we can send this to the feed forward network. So that will be passed to the second layer. So the story so far, this was our sentence, thinking machines. We embed each word, we calculate the embedding, right? And once we calculate the embedding, we add the positional embedding, which is not shown here, but we add the positional embedding, and then we number of multiple heads, we calculate the query key and weight matrices. So we multiply this X with weight matrices, right? So this weight matrix is nothing but it is saying that we are passing through a neural network of some size. So we multiply it, we calculate query key and value for, let's say, one head and then the second head and so on, all the heads, from which we get the Z matrix. Then we multiply with the weight W to produce the output of the layer. If we are saying this is the first encoder layer, then we say it is X. However, if okay, so one is for embedding of thinking and one is embedding of token machine. If we have, let's say, okay, if this sentence is an input, let's say, for example, the sentence is written, this is our input sentence. So for this, you have one vector, embedding, and so on. So the idea of adding positional encoding is to add the position awareness in the data, so that if the text was machine thinking instead of thinking machine, the encoding should be different. So how it is does, for example, lion killed the man or man killed the lion, they should be encoded differently. So for each position I in the sequence, what we do, we compute a vector where each dimension j is the function of I. Right. So let me give you a simple idea. What we do, we use cosine, we use sine and sine functions, and specifically for assuming for the even position of them in the word embedding, even positions we use sine, and for the odd we use cosine. And this function create oscillating pattern that vary with the positions. And this way model learns the relative position and distance between the tokens. So, and this ensures that these positions are position information is reserved and preserved throughout the model learning part. So we have an input, we calculate the embedding, we add the positional embedding, and we get the embedding with time signal, you can say, which is having position information as well. And this is passed to encoder 0, which have self-attention mechanism, which gives you output, and then you pass it to the encoder 1 and so on. Apart from self-attention where you get the Z, you have add and normalize layer. So basically, this layer is used for the normalization purpose. So the training of the deep neural network becomes easier. So computationally, it should not be uh, if inefficient. So what we normalize this, we normalize the output of the encoder uh, of the self-attention networks. So after each sublayer, for example, multi-head attention or FFN, the input to the sublayer is added to the output. And this is basically the residual connection. And then the layer normalization is applied, which normalize the activation across the features for each position. So this is basically the normalization purpose. This basically for the normalization purpose, so that computation can become easier. And this also helps in vanishing gradient problem and ensure the gradients flow smoothly through the network. In simplistic terminology. So encoder layer in the transformer have multi-head attention layer, feed forward, and add a normalization layer. So multi-head attention, self-attention basically computes the contextual representation, feed forward, which adds the non-linearity, and this is for the normalization so that to stabilize the training. And these components are basically stacked to form the full encoder. The encoding part में यही होता है. So this is the encoding part. Feed forward is for the non-linearity basically. It is simple that it is as similar to the neural network that you have studied. You can think of this output of multi-head attention is given to the feed forward basic neural network to add in the non-linearity. So this becomes the portion encoder side. Inside around the side of decoder, you have masked multi-head attention and encoder decoder attention and feed forward and add no. So these two are the same, similar to the encoder side. In the multi-head attention, we had a diagram of architecture. Where was it? Okay, so this was. So this output embedding, basically when you are during the training time, you have vast amount of data, you have input output pair on which you are training. Let's say you have a machine translation task, right? So you have input corresponding to you have ground truth, basically the output. So this output embedding is given. Someone have asked me why it is shifted right. So basically the reason is uh, the output that is generated is generated one word at a time, right? So the output during the training, what we do, the output sentence, we shift it right. For example, I like this movie in one language, and in some other language it might be represented by something other. It is shifted right, and a special token uh, uh, like SOS, the start of the sentence, is added here, and the sentence is shifted to right. And suppose we having a length of 4, so this become your the output. SOS, I like this. So that marks, because we are going to use masked multi-head attention network. Mask means when, let's say, it is generating like, it should only focus, or it should only depend on the previous uh, previous outputs like I. So future output tokens are basically output values are masked using infinity value. So what we do in decoder, we use masked multi-head attention to ensure the auto-regressive generation. Auto-regressive generation means the same thing, that when we are generating kth token, the decoder should only attend to the tokens up to kth minus 1. So first kth minus token, not the future ones, because and this is achieved by the masking the attention score for future tokens. There it is. So we are masking it, and we are masking the attention score for future tokens, and by setting up the negative infinite value, and when the softmax is applied, they become 0. Right. So this way, model learns the basically learns and predict the each token based on only what has came before it. So in the previous tokens that it has seen. So output pair, which works as an input to the decoder side during the training, again uh, added with the positional encoding for the same purpose, and the masked multi-head attention, which is similar to self attention, but the only part is which we are basically uh, we don't want to the generation of the ith token should not depend on the future tokens, only depends on the previous tokens we masked it. Normalization, then we add it for make it computationally easier, and then let me go to the same slide. Yeah. And then after a mask attention layer, you have encoder decoder attention layer, where output of the top encoder is transformed into K into V. So the result that you have got from the encoder side, you again transform into K into V matrix, and you give it to the decoder. So for example, okay. So okay, so it is same. So here you can see after the encoder, that the last output that you get. So this basically the last output that you get. Using this, you again generate the key and value pair. Key and value pair is passed to the decoder side. That's why this particular layer is called uh, encoder decoder attention. So for each token the decoder is generating, it computes the attention weight over the entire input sequence which it has received from the encoder size, so that it focus on the most relevant part. So this you can see. So this gives to decoder, and then previous out. So when I was generated, and once the I was generated for the next output, again it takes the key and value and the previous output, and it generates the next token. So that this key and value pair make sure uh, which part is relevant to generating M and so on. And this, so there are two phases. One is the training phase and one is the generating phase. During the generation phase, it uses auto-regressive decoder. Basically, the decoder generates the output sequence auto-regressively. Means it predicts one token at a time, and it uses its own previous prediction and it uses its own input. So initially, that's why that's right shift was there, because for generation of I, the previous token will be SOS that we have added by shifting it right. And for generating M, the previous token will be IN SOS. So during training, this this is called teacher forcing, where the true output sequence is fed as an input to the decoder. So during the training, since we have input pair and output pair, we give it to the decoder. During the inference time, what we do, model uses its own prediction. We just give the a special token or maybe any token, and it produces and it generates its own sentence until the end of the sequence token. And again, after decoder at the end, we use linear and softmax layer, which basically gives you the probability over all possible tokens, and just say the probability which is the highest is basically the your predicted token. So this softmax basically gives you the output. So though initially it is not trivial to understand how transform works, but at least I hope you understood some of the key points here. One is why you are using positional encoding, and instead of generating one by one in a sequence way, we are taking all the inputs together and we are creating alternative approach by creating matrices in key value and query, and using those we are making computation to generate the output sequence. And it has two phases. One is the training phase, where during the training we fed the data as an input and true output, and during the inference time the decoder only generates the output. So you can think of during the training we collected the large or vast amount of data. Let's say from Wikipedia we collected all the data and we trained the model by giving the input and output pair, and we train the model. And once it is trained, you just throw down the encoder, and using decoder only you just generate the data. So you start typing, let's say, or you give some random input that can be your SOS, start of the sentence, and the decoder generates the sequence of the sentences. So the training requires large amount of data, and the idea that I have given just right now, the collecting the data from the Wikipedia and so on, these GPT models are basically trained in this way. So this training of this transformer model required large data set and computational resources, because at the end inside we are doing matrix, basically algebraic operations. So this needed lots of computation, and you need GPUs and TPUs for this. So this is the intuitive idea of how transformer works. I hope you have slight idea how this works. So for machine translation application, encoder should not be thrown. So I was okay. So depending on the task, it has different uh, architecture of the transformer. For example, let me directly go to this. Okay, so there are different variant. In case of you might have heard about BERT language model, which is given by the Google, which only uses encoder part. And most of the tasks like classification and question answering, the BERT has been used, where only encoder part has been used. So it uses only the encoder for tasks like classification and question answering, whereas GPT, which is for the text generation, which is used for generative AI, it uses only decoder part. Once it is trained, after it is used only decoder. So it uses only decoder for generative text, like text completion and language modeling. So it depends which what is the task at your hand. Usually you train using feature forcing approach to make it decoding parallel. Typically you use cross entropy loss, and you measure the difference between predicted and true output. This becomes your loss function. And you have different applications like machine translation. So the Google the machine translation uh, solution that Google have given uses Google neural machine translation that do this task, that uses transformer. T5 and BERT is used for the text summarization. Question answering, again the BERT transformer is used. Language modeling like GPT or GPT series are the application of the transformer. So what, in summary, what are the advantages of using transformer? One is basically parallelization, because uh, unlike generating sequence to sequence, you are able to do the computation in parallel, which makes them faster than the RNN. And it can handle long range dependency because of the self attention mechanism, which captures the relationship across entire sequence. And obviously it is scalable, which can handle very long sequences with sufficient resources. And obviously it has good performance compared to the other most uh, previous NLP models. However, there are some limitations as well. Obviously, those algebraic operation requires high computational cost. Data requirement is another challenging uh, challenge you have, and interpretability is another issue, which basically not only with transformer, it is there with all the deep learning models, because usually all these deep learning models are considered as a black box, and how they are learning and how they are understanding uh, it it makes difficult to decisions. So the key concepts, I hope by understanding the transformer, you must have understood uh, what is transformer, what is encoder and decoder, and the self attention mechanism is there. The concept like positional encoding, at least you now you have intuitive idea of it. Multi-head self attention, auto regressive code decoding. So for decoding one token at a time, and it should only focus on the previous tokens. We mask uh, the self attention scope, and then encoder decoder attention. So these are the key concepts that we had studied, and from there we it has been moved to transformer to the LLM side. So this transformer, with their ability to process sequences in parallel and capture long-term dependencies, this have become the foundational for the large language models. So most of the large language models are, all the large language models are basically based on transformer. And by scaling up the number of parameters, increasing the number of heads, and adding more layers, encoder decoders, basically, and training on the massive dataset, transformer have evolved into LLMs. So LLMs are known as a large language model. So large means they have billions of billions of parameters and having huge number of layers in it. And once it is trained, it excels on the task like text generation, translation, and question answer. For example, GPT-3, which was proposed, have 175 billion parameters, and it can generate human-like text, perform translation, and even write code with minimum fine-tuning. And you have a BERT, which is proposed in 2018, which uses bidirectional transformer encoder pre-trained. So there is no decoder, there is only encoder which is used a large purpose. And if you want to perform text classification or sentiment classification, for example, fake news detection, any task which involve text, and you want to perform some classification, then BERT is one of the best models. T5 is there, which uses both encoder and decoder, like machine translation task, and it how it works. So it transforms all the NLP tasks as text-to-text problem, converting from text to text, and then it uses encoder decoder transform. Obviously, some of the key enablers like scalability is because transformer can perform parallel processing. So that's why training can be done on the billions of parameters, and it enables. This is one of the important benefit of transformer. It has enabled the transfer learning, which was not there in the language side. Now what we can do, we can train. So we can use pre-trained models like BERT, GPTs, and all, and we can use it for and when transfer learning introduced in NLP area, then this large language models have appeared and have become quite popular. Obviously, there is hardware enhancement has been huge support for it. So the many GPUs and TPUs are evolving that support the computational demand of training large language models. This is just a history. When until this point of time, the transformer have not been introduced, there is the NLP area was lagging, or computer vision was more popular in deep learning instead of natural language processing or text generation side. However, once the transformer have been introduced, you can see a lot of GPTs models and other models have been proposed by various organizations. So, any questions? This is the end of this session. So let me do one thing. What we can do, I had prepared a notebook. Okay, so I prepared an hands-on notebook. So instead of, since we don't have time, so what we can do, I'm sharing you this notebook. You run it on the Google Colab. I will explain you uh, each term, each portion of the code line by line. So let me share it with you. So I have shared it. Did you all receive it? Okay. So okay, I have to share it. Okay, I think I could not find in WebEx. So what I'm doing, I'm dropping that file on the WhatsApp group. Okay, so those who are in the WhatsApp group, they can see I've shared a notebook file. Uh, since demonstrating transformer or heavy architecture, it's not possible because of the training time and the computational resources needed. Uh, Instead of that, to give you a clear understanding how language model works, I have created a simple text-to-text generation model using LSTM. So that I have shared. What you can do, since I was thinking to discuss this in detail. So since we have shifted this to tomorrow's lecture, what you can do, you just go through this notebook and run it on the Google Colab, and each section try to understand what is happening. And even if you do not understand, we are going to discuss this in the next session, that is tomorrow. So in the tomorrow hands-on session, we are going to start with this notebook, and then we are going to see some of more pre-trained models from Hugging Face to generate text to image or text to speech. And we are going to see how you can use the pre-trained models from there, and you can use it in your application. So if you have any questions, you can ask right now. Okay, so I hope you all got the intuition of language models and transformers and sequence to sequence models. Uh, okay, if there is no question, then we can resume after 15 minutes for the next session. Thank you.